So if we're still gonna have omega and t, now can you identify where's the curve when voltage is 0? So previously we did this when voltage is either positive 12 or negative 12 volt, and they're symmetric there. Then you can imagine the line which is parallel to them, but cause the origin gonna be the curve with 0 volt, right? So let's draw that. So if you apply 0 volt constant voltage, so that's a curve, speed torque curve under that constant voltage. And so this is line as it would divide this space into two regions, right? On this region, upper right region, and you will have all positive voltage. And below this line, in this region, you're gonna have negative voltage, right? Make sure you understand that. And the slope of this curve can be written as negative R divided by the torque constant square. Let's first look at the mechanical power in this plot. Let's define, since the omega and t will divide this region into 4 parts each quarter. Let's label this 1, 2, 3, 4. And for mechanical power, if we look at 1 and 3, what's the mechanical power going to be? What's the sum of mechanical power? As a reminder, mechanical power inside of DC motor equation, that is torque times omega, right? So P mechanical equals T times omega. So only if you have both T and omega are positive, you will end up with positive mechanical power. Or if they're both negative, you will also end up with positive mechanical power. So let's look at region 1. At region 1, we have both positive T and positive omega. So we're gonna have positive mechanical power. Same thing for this quarter here. We have both negative omega and negative torque. So at both 1 and 3, we're gonna have positive mechanical power. That means in these two regions, if you give the motor is generating mechanical power, producing power. Producing mechanical power. And now let's look at region 2 and 4. If you look at 2 and 4, and at 2 we have positive torque but negative omega. At 4 we have positive omega but negative torque, and therefore we have negative mechanical power. And this means the motor consumes mechanical power. And therefore the mechanical power under 2 and 4 were acting kind of like a damper. And we can talk about that later. But this is a mechanical power. Now we know for DC motor we also have electric power. And how this electric power gonna look like? So where do we have, first let's look at what's the equation for electric power. That equals voltage times current, right? So when our voltage, both voltage and current are positive, both they equal to greater than 0. So that's the region. How do I draw that? Draw this. That's this right shadow region. So the red shadow region, it's when the electric power greater than 0. That means we're consuming electric power. And where is our negative electric power region? Use different color. Use blue. That would be the region here. What does that mean when we have negative electric power? That means we're producing electric power. So if the current times voltage is less than 0, and if your motor is running that region, that means we're producing and our motor acts like a generator. And also it's called regeneration. If you have a hybrid vehicle and when you step on the brake, and that at that time your car is regenerating all electric power. That's also called regenerative braking, I think. Generation. It's called regeneration. So if we want to have a motor and we want to use that motor as a generator, for example, for our electric car application, you want that car to regenerate as much as power as possible to recharge the battery, and that slope there, the slope on the curve becomes very important. As you can see, that's slope. If the slope is very deep, then this region, this is dark blue region, going to be small, which means you're going to have a smaller running region for to regenerate electric power. So under regeneration, that slope is very important. Slope is negative r over kt squared. And if either r increase or KT decrease, and that will give you a very steep slope. So your curve gonna move to that direction, and that will give you a smaller region for regeneration. Okay. Next, let's plot the power out from the motor to see where on the curve we're gonna have the maximum power output, since that's something we want to figure out. So now let's keep having this omega torque. But on the other side, I want to draw a vertical line to represent this is our power output, P out, from the motor. And the speed torque curve, which is just a straight line with a slope. This is the maximum velocity, which is a no load speed. And here we have store torque. And if we want to draw what's the power output look like, the curve gonna look like this. So this right curve gonna be the power output. It should be a more smooth curve instead of like this. And that point here is the maximum power output. It should be a parabola. And the corresponding velocity here, it's the, oops. So that maximum power will have a corresponding velocity. And that point is half of omega, which is the maximum no load speed divided by 2. And the corresponding torque on the x-axis is going to be 1/2 of the stored torque. And that point is our maximum power output. So if you want to operate your DC motor, and that's the point you want to operate your motor at. And we can easily calculate what is the maximum power output. It's going to equal to power, mechanical power. Since here we're talking about mechanical power, so that's the product between T and omega, right? At that point, at the maximum power output point, we have the corresponding T omega divided by 2 and T store divided by 2. So we're going to have 1/4 T store times omega. So that's the maximum power output. And sometimes this maximum power output, it's not the region you can run the motor at continuously. If we go back to this plot, we mentioned there are 2 regions, and you're able to run your motor in this region 1 and continuously for a long time, but you're not allowed to run your motor at region 2 for a long time. So sometimes this maximum power output, and it's not in the, it's in the intermittent region. So you cannot run that for a long time. Okay, And here, I think it's a good time to talk about efficiency of the motor. Efficiency of the electric motor equal to what's the power input versus what's the power output. What's the power output over input? So the power output can be a torque times omega. The power input, which is your electric power, current times voltage, and times 100%. So that's the efficiency. And electric motors really have a much higher efficiency than internal combustion engines. They're usually greater than 80% of efficiency for electric motors, DC motor. And those, if you want to reach a high efficiency, and a good suggestion is to run your motor at low speed and a low torque, high speed, excuse me. Low torque, high speed. So that's the region you can run your motor to reach the best efficiency. Okay. Let's see what's next. All right, and one more thing is, since here, when we introduced the DC motor equation, we didn't include friction. If we include friction, and the friction gonna add more difficulty to for the motor to turn, and so the actual curve for friction, if you have friction inside, and your curve gonna start at a, let's call this omega pi. So the maximum speed of your motor gonna lower than the ideal no load speed, because that friction you need to overcome. And usually that curve, that motor curve will start from there. So you lost some of the maximum speed due to friction. And that corresponding point, that is the torque you need to overcome friction. Okay. So those are some important points about DC motor. Next, we talk about so much about those technical details and equations and curves. Now let's take a look of a real DC motor data sheet, and look. Then we can go through the data sheet to see how are the data. How is the data sheet is related to the content we're talking about today. So here I have a screenshot of the DC motor, and this DC motor is from Maxim Motor Company, and it listed two different types of motor under the same nominal power, which is they're all 10 watt, but this company offers two different configurations, and one motor it's can run at a nominal voltage of 9 volt. Another one has nominal voltage of 12 volt, but they all offers 10 watt. So let's take a look at this data sheet, and let's first look at why we have two different types of motor, and they all offer 10 watt, but they are running at different nominal voltage. And if so, one reason though they could have different voltages because the how much wire they use for their coil and the thickness of the wire. So it could be the one with 9 volt The one with 9-volt nominal voltage could have very thicker wires, the wires for coils, and they could have fewer loops in their system, in the coil as well. And therefore, and for this 9-volt 10-watt DC motor, it may require more current because the thicker wires can hold more current flow, and it requires less voltage. That's why it has 9-volt. It only requires 9-volt. But as a compensate, you need a little bit large current to reach the maximum power output. And for another motor that has 12-volt as nominal voltage, and it could have thinner wires and more loops. Therefore, it needs a little bit less current but require more voltage. And another place we can see that is that's nominal speed, nominal voltage. And if we look at here, number 10, terminal resistance. That's in unit of ohm, that's a resistance. If we compare between these two motors, the one with 9-volt has a little bit lower resistance, which is 1.23 ohms. Another one has 2.18 ohms. So the one with 12-volt, it has a higher resistance. That's also verifies what we just talked about here. If the 12-volt one has thinner wires and more loops, that therefore there be more resistance. It's showing there. And next parameters we can look at is this terminal inductance, number 4, and that also tells us, if you can see here, that's number 11. The 12-volt motor has a little bit higher inductance. That means more loops, right? More loops in the coil. Next, we can look at the torque constant. We mentioned this torque constant is one of the most important parameter for DC motors. Torque constant is defined as T divided by current T over I, right? So as you can see, the unit here is million-newton meter per amp. The motor with higher voltage will give you a better torque, a higher torque constant. Next, we can look at this constant speed, and we didn't talk about constant speed, but however, this speed constant, it's the same thing as torque constant. So where's this speed constant come from is, if you remember, we introduced two different units for the torque constant, K. And one of the unit is Newton meter per amp, we just mentioned that. Another unit is SI unit as voltage times second per radian. And if we take 1 over K for the SI unit, you flip radian per voltage times second, this can be converted to what we have here, RPM per voltage. Since radians per second can convert that by revolution, but convert second to minute, then you will end up with RPM per voltage. So number 12 and 13, they're pretty much the same thing, but in different units, if that makes sense. Then next we have this speed torque gradients. So that's a slope we mentioned in the speed torque curve. That slope, remember that slope also determine how much regen you have for the regeneration. Slope equals negative R divided by torque constant square. So that's what this speed torque gradient is for. And next here we have mechanical time constant. So this mechanical time constant, as you see, that it has the unit millisecond. So that's that's the time it takes if your motors start from 0 RPM, and you give it a nominal voltage, which is either 9 or 12 volt in this case, and it will take, in this case for 9 volt motor, it takes 4.37 milliseconds to increase the speed from 0 RPM to 63% of the no-load speed. So 60% of no-load speed, that's a 60% of the maximum speed in this for this motor. And for the motor with 12 volt and takes a little bit less, 4.25 millisecond increase from 0 RPM to 63% of the maximum speed. And where's the maximum speed on this data sheet? Yes. So the no-load speed, that's kind of the maximum speed of those two motors. They're both around 5,000 RPMs. And next, you can look at, see the data sheet also give you what are the nominal speed. That's kind of the suggested speed, and nominal torque, nominal current, and starting current. Okay, so here it's something maybe interesting to you. If you look at this no-load current, number 9, and that's milliamp, that's around 30 something, and this one's 26 something milliamp. So why there's no load? If there's no load, why the current is not 0? And that is because there's a friction inside of the motor, so you need a little bit of current to overcome the friction torque inside of the motor. And another current here is this nominal current and in the unit of amp. So in order to run these two motors, then you need about 1.5 amp to run these two motors. And here you will see another current that's called starting current, number 11. And if you compare this starting current is around 7.31 for this 9 volt DC motor, and it's around 5.5 volt amps for this 12 volt motor. And if you compare this starting current with the nominal current, it's almost 5 times higher than the nominal current. Why so? So that tells you at the beginning, when you try to run the motor from 0 RPM to a certain speed, and the current is a large current is needed at the very beginning when you run the motor from steel, and that current can be much larger than the nominal current. And so related this to electric cars is when the electric car is parked, you step on the gas pedal, and that's the moment it consumes most of energy, draws a lot of power, current from the battery pack. That's the moment your battery is starting to lose power, lose energy. And that's also this number 8, starting current, and it's also the same current when your motor is stored. So when you hold the motor and that store torque at that point, and that's also the current going through the coil without turning the motor. So all of this 7.31 amps were going through the coil, heating up and to burn out all the coatings to cause the failure of the motor. See what my notes, what other things are there. Okay. Number 10, let's see what's number 10 on my notes. Yeah, number 10 on the notes, nominal current and that term is related to the torque constant. As we remember, torque constant equals T divided by current. So if you have this nominal current, you have the torque constant, you are able to find what is the nominal torque. So if you do the calculation, you will find the nominal torque from there. All right. Here, I think now we should have a good understanding of brushed DC motor, and also we look through the data sheet for two different types of DC motor. And that's all for today. And so remember, on Thursday, I want you to send me, how about this, after today's class, I want you to send me the electronic version of your first project proposal. So I can take a look and write some comments. So on Thursday, I will talk with each group individually and then give you some guidance and comments for your final report. All right, that's all for today. Any questions? If you don't have any questions, feel free to go offline and enjoy your day.